Hello, and in this video we'll take a look at A-level physics, specifically for EDEXCEL. We'll take a look at electrostatics and more importantly covering the topics of the electric field strength, and Coulombs law. So we need to understand these three specification points. Specification point 108, which states that we need to understand that an electric field is defined as a region where a charged particle experiences a force. Specification point 109, which states that we need to understand that the electric field strength is defined as the force per unit charge and be able to use this equation. And specification point 110, which states that we need to be able to use the equation for the force between two charges, which is given by Coulombs law. So starting out with Coulombs law, well, what is Coulombs law? Coulombs law basically states, or it considers, the electrostatic attraction or repulsion between two stationary charged particles, which is given by the following formula of F is equal to the product of Q1 by Q2 divided by 4 pi epsilon naught r squared, where Q1 and Q2 are the charges of each individual point charge. Now it's important to note that the reason for the modulus symbol being applied is that one of the charges can be negative, whereas the magnitude of the force is always positive. So to end up with the right answer, the absolute value has to be taken for the product of Q1 and Q2. The quantity epsilon naught is basically defined as the permittivity of free space in a vacuum, which possesses a value of 8.85 times 10 to the minus 12 farads per meter, and r squared is the distance squared between the two point charges Q1 and Q2. Now it's important to note that any given electrical charge creates an electric field which extends outwards in all directions and emanates all of space. Considering a positive point charge Q1+, the electric field lines extend outwards in all directions, and if a positive test charge such as Q is placed within the vicinity of Q1+, it will experience a force as a result of the electric field present. So if we have a look at this following diagram here below, just to recap this one more time, we have a positive test charge Q1+ being present with the electric fields of Q1+ extending out in all directions. And for this specific diagram, we'll just consider the electric field in the horizontal orientation. And the positive charge labeled by lowercase q is along the same orientation as the electric field produced by Q1+, so it will experience a force due to Q1+'s electric field. Now it's also important to note that in electric fields you can also have electric field strengths, which means that the test charge Q will experience a force as a result of Q1+'s electric field divided by the electric charge of that test charge Q. And the electric field strength has the following formula of force per unit charge with the units of newtons per coulomb. If we take a look at this question, for this question, it states that we need to draw the lines of the electric field representing the proton. So it's important to note that for a positively charged particle such as a proton, the electric field lines extend outwards from the particle. Now note, if this was a negatively charged particle such as an electron, the orientation of those field lines would reverse, so the electric field lines would point towards the particle if this was negative such as an electron. The second part of this question asks to calculate the electrostatic force on an electron in a hydrogen atom, and it's given us the average distance between the proton and the electron. So this is where we apply Coulombs law to determine the force. So we state our quantities that we know. So we initially state the charge of the proton, which is given as 1.6 times 10 to the minus 19 coulombs. We also state the charge of an electron, which is given as minus 1.6 times 10 to the minus 19 coulombs. We are given the distance of 5.4 times 10 to the minus 11 meters. We also apply the constant, which is the permittivity of free space in a vacuum, which is given as 8.85 times 10 to the minus 12 farads per meter. Substituting all of these values into Coulomb's law, into that given formula for the force, we end up with a value of 7.9 times 10 to the minus 8 newtons. Considering this next set of questions, it is said that an electron is basically accelerated from rest by a uniform electric field, and given that the electric field strength is 1.2 times 10 to the 5 newtons per coulomb, calculate the following: the force experienced by the electron. So if we use the formula for the electric field strength, which is defined as the force per unit charge, and if we rearrange that to make force the subject, then we essentially multiply the electric field strength by the electron charge, which gives a value of 1.92 times 10 to the minus 14 newtons. So that's the force experienced by the electron. And for the next part of this question, it asks us to basically calculate the velocity of the electron after 4 nanoseconds. Now, it's important to note that the quantity which relates both velocity and force is acceleration. So for this second part, we have to use F equals ma, rearranged to make a the subject of the formula, and we substitute in the value for the calculated force from the previous question, which is 1.92 times 10 to the minus 14 newtons, and we divide that by the electron mass, which is given as 9.11 times 10 to the minus 31 kilograms. And we end up with a value of 2.11 times 10 to the 16 meters per second squared. And then if we use one of our Suvat equations, which is given as v is equal to u plus at, we know that the initial velocity is 0 since it's accelerated from rest. We can then consider v being equal to at with the acceleration that we've just worked out being 2.11 times 10 to the 16. And if we multiply that by 4 nanoseconds, obviously making sure that we convert it into the standard unit of seconds, we end up with a value of 8.44 times 10 to the 7 meters per second. For the third part of this question, it asks to state the displacement after 8 nanoseconds. So for this part, we use S is equal to ut plus a half at squared. So we already know that the initial velocity is 0, and we can kind of just ignore that first part and focus on the second part, which is the half at squared. We've already worked out the acceleration, which is 2.11 times 10 to the 16. And if we apply the time that's given in the third part of this question, 8 nanoseconds, and we convert that to standard units and then square it after multiplying it by the acceleration and then multiplying it by a half, we get a value of 0.6752 meters. Thank you for watching. I hope this video has cleared any questions anyone's had regarding the electric field strength, and Coulombs law. I appreciate my viewers. Please like, share, and subscribe, and stay tuned. Thank you so much. Goodbye.